two metal balls stuck to a magnet. One ball is held very close to the magnet, while the other is slightly further away. When you try to pull the metal ball that is further away, much less force is needed. But when you try to pull the metal ball that is closer to the magnet, you need to use a lot of force. This happens because the magnetic attraction is stronger at a closer distance and weaker at a further distance. So do you remember when we studied atoms in chemistry? These subparticles called electrons in the atoms also require certain energy to be removed. This is what we call ionization energy. Ionization energy is the minimum energy required to remove an electron from an atom. When atoms want to become ions, they must remove electrons. However, there is a strong attraction force between the nucleus and electron that pulls the electron towards the nucleus. This attraction force is known as effective nuclear charge, or ZF. In order for the electron to escape, a certain level of energy must be supplied to fight the ZF. Let's take a look at the periodic table. Across a period, ionization energy increases. As we move from left to right, electrons are added to the same main energy level and similar orbitals, but the number of protons in the nucleus increases. This increases the effective nuclear charge, meaning the nucleus pulls the electron probability cloud more strongly towards itself. The size is also getting smaller. Therefore, the smaller size and stronger ZF makes it harder to remove, just like a magnet holding a metal ball more tightly. That is why chlorine has a higher ionization energy compared to sodium. Now going down a group, ionization energy decreases. Each step down the group adds a new principal energy level, placing the valence electron in an orbital that is further from the nucleus on average, so the atomic size also increases. At the same time, inner electrons shield the outer electrons from the nuclear attraction. So because of this shielding effect, the valence electron experiences a weaker effective nuclear charge. The larger size and weaker ZF is just like a magnet pulling a metal ball from farther away. Therefore, less energy is needed to remove the electron. Now that is why sodium has a higher ionization energy than potassium. However, some elements do not follow the general trend. For example, beryllium and boron are in the same period. According to the general trend, ionization energy of boron should be higher than beryllium. However, scientists discovered that actually the ionization energy of boron is lower compared to beryllium. Why is that so? Let's take a look at the orbital diagram of beryllium and boron. So beryllium's valence electrons have fully filled up s orbital, while boron's has one valence electron in a p orbital. Try to imagine the orbitals as a seesaw. In order for the seesaw to be balanced, they must be filled with equal mass on each part. Same goes to orbitals. If they want to achieve stability, electrons have to be filled either half or fully. Let us compare between beryllium and boron. For beryllium, the s orbital is fully filled with a pair of electrons, making it more stable. However, for boron, there is only one single electron in the p orbital. This structure causes it to be less stable. Therefore, boron has a lower ionization energy compared to beryllium. Nitrogen has a half-filled p orbital arrangement, which is relatively stable. However, note that oxygen has only a partially filled p orbital. When we imagine it as a seesaw, the electrons appear to be unbalanced and less stable for oxygen. Therefore, oxygen has a lower ionization energy than nitrogen. Let's take a look at some of the examples. Lithium is commonly used in batteries because it has a low ionization energy. Its outer electron is weakly held, allowing electrons to move easily and produce electric current. Sodium reacts violently with water because it loses electrons easily. To conclude, ionization energy helps explain trends in the periodic table, chemical reactivity, and the technology we use every day. You can see ionization energy as every atom's superpower. Remember, chem is tree, chem is try. Try to have fun. Bye!